Hi. It's been 5 weeks since I recorded the intro for this video. Lots changed since then, so it's time to actually update that. What's been going on for 5 weeks? Well, my wife has a cookbook that's being published, and I had to help her get the rest of the edits done for that. It's going to be published on August 19th. More information on that in the next video. I also had all of the components delivered for the Control ROM modules as well as the PCBs. I'll have more on that in the next video as well. I'll be building that out starting in the next video. And then I also had my annual family vacation, 2 weeks in the Eastern Sierras camping. It was a good time, fantastic memories. But now it's back to reality. So what is it that I want to get done in this video? Well, I need a program ROM for the emulator, and that's the focus of today's video. It's going to end up being very similar to the RAM, except I'm not going to have a write capability associated with it. And I'm also going to have to preload the contents of that off of disk. Other than that, it's going to be a pretty straightforward copy and paste of components that I already have. The whole point is to get that working so that I can run code to execute the tests that I've built so far on the emulator, and make sure that the emulator is actually behaving exactly the way I need it to. Well, that's enough blabbing. Let's get into that.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
Okay, for the program ROM, the device I want to emulate is an AT28C256. This is a parallel EEPROM. One of the devices I've struggled trying to find. Now, they are more readily available now than they have been, but I'm going to stick with my current solution, at least in hardware. For this is going to be a temporary solution specifically for the emulator, so this is going to be what I'm going to emulate at this point. Here is the pinout for the DIP package that I'm going to be emulating. This is the SRAM that I've been using. This is the AS6C62256, and it's also the SRAM I've been using in hardware. And this is the pinout configuration of the DIP package here as well. Okay, now, if I take the two pin configurations and set them side by side, you'll notice that they exactly match. So, Adam, why can't you just use SRAM as your base? And the reality is I probably could, but I do want to make sure that I have a discrete IC for this. I want to make sure that I can't do any particular updates on it and mess up the contents of the program ROM. That's going to be further down the line that I actually take that on. So the write enable pin that's on pin 27 is going to be explicitly tied high. Really, it's actually not going to exist in the pin configurations and the interfacing for the AT28C56 IC because I don't want there to be anything that allows it to write. So I'm going to completely remove that code, which means it's a good candidate for copying the SRAM and performing my updates. Let me start on that coding, and I will come back and give a quick code review of what the changes are. Okay, well, it compiles. I guess that's step one. Now, other than a few minor changes, there's really 4 source files where there are significant changes related to getting the AT28C256 emulated. The first 2 are the actual header and source for that particular IC. And again, I did a copy of the SRAM and stripped out things that I didn't need. For example, pin 27, which was the write enable inverted, that's been pulled. A couple of things related to tracking state and the reference back to its source EEPROM if it was used. A couple of hold states, write enable, whether or not I'm updating, and then all of the signals, all of the slots associated with getting updates off the bus into the SRAM all go away. So those are just commented at the moment. but the actual source has been stripped down and cleaned up pretty significantly. In the application, I also added the ability to take a command line parameter for the folder that contains the program ROM that needs to be executed. And then in the actual application source, I've moved the constructor in here, and I'm now saving that folder location and retrieving that so that if I don't specify a command line parameter, it will pull the last value and re-execute the last test. I don't have a way of testing this just yet. I do need to create a module for the control ROM, and that's going to be next. And so I need to kind of roll up my sleeves and figure out exactly what needs to be there. It's going to mirror pretty closely what I've got on the breadboard now. So let me get going on that. I will get that Program ROM module built out, integrate that into the emulator itself, and then prepare to run a test. We'll test this together. Okay, here's the new memory module in the bottom left-hand corner here. The address bus 1 is presenting address 0 out, and that is the memory contents for address 0 for this particular test from episode or video 74. But something's still not right here. Now if I step and iterate, address bus 1, this loads the next one, but what is in the fetch register shows up here, and that really should be matching what's in the instruction register. I believe what's latched is what was from the previous instruction. So the previous instruction was 1.1, and let me go check that. Yeah, so instruction 1.1 was to move the 0 register into R1, and so the control ROM 9 bit 7 is being presented along with control ROM 7 bit 7. So control ROM 7 bit 7 is up here. That is just the program counter increment. Control ROM 9 bit 7 is to load a value into R1. So what do I have here? I have the control ROM control, which is presenting what is on the fetch, but the actual flags here are the actual control bits associated with the previous instruction. That makes for a confusing and incongruent system. So what I need to do is I need to change it so that what is on the control ROM control, which is actually not latched, to match what's on the instruction register. And that means that the instruction register has to have some outputs. All right. Let me get that cleaned up so that I can track what's going on in the emulator a little bit better. But above and beyond that, this does appear at this point to be working reasonably well. What I have to do is I have to spend some time actually looking at it and making sure. All right, let me get some changes made. I'll come back. I'll show you what the end result is here. Well, that didn't take very long. What didn't take long, Adam? It didn't take very long to find a flaw in your newly minted PCB. What flaw is that? Well, the flaw is that the LEDs are always going to be out of sync with what's being presented on the actual control. So the LEDs on the control ROM control module serve absolutely no purpose at all. Okay, so what exactly am I talking about here? Well, in the control ROM control module, there are LEDs, but those LEDs are actually sourced and sourced correctly between the fetch register and the instruction register. Effectively, what we're doing is we're capturing the instruction right before the instruction itself is latched. And at the same time the instruction is latched, the EEPROM has been queried for the correct data, and each of the 16 control ROM modules themselves all latch the contents at exactly the same time. Well, what does that mean? Well, the LEDs in the control ROM control module can go away completely, and that then allows the instruction register to actually drive the meaning of what's in each of those 16 control ROM modules and which lines are being asserted there. Let me make that change in the emulator there may still be an additional issue to solve, but I'm going to start by removing the LEDs out of the control ROM control module first. Okay, so here's the change with those LEDs removed out of the emulator. Now, it's not perfect. For example, if you watch closely, the first instruction is going to be executed twice because it's in the fetch register, moves up to the instruction register, the same instruction is fetched a second time. When I first launch it, it does 1111. It executes twice. I'm not going to stress too much about that at this point. I've got an issue logged in GitHub that I need to develop out a proper reset circuit for the emulator. I don't have a proper reset circuit yet. I need to work on that. So in the meantime, what I'll just do is I'll put a no-op as the first instruction. I'm going to steal a page out of James Sharman's book there. He had that for the longest time just to make sure that he was able to reset down his circuit, and I'll leverage his idea for mine as well, or at least my emulator. There are some instructions, such as this load here. This is loading a value into R1. R1's not wired up in the emulator yet. But for this instruction, bit 7 on control word 4 should be set. I have not researched to try to find why it's not. That particular signal on control ROM 4 bit 7 is instruction suppress. So in the emulator, when I'm loading a constant into R1, word is not enabled, or I'm sorry, the control line is not enabled in the control word, and I'm not getting an instruction suppress here in the fetch register. Got a few things to sort through. The big deal here for me is going to be making sure that each one of the instructions that I have written actually present all the correct bits on the control word and determine why it's not if it's not. So I'm going to write a purpose-built test to iterate through all the different instructions I've got to make sure that everything is actually being set properly. One of the things to keep in mind here is there now are 3 different things that could be a problem that I've got to discern. The original 2 were there could be an issue with the actual logic and therefore the hardware is not going to work. The second one from before is that there could be an issue with the emulator where the emulator is presenting a problem that may or may not exist in real hardware. Or put another way, I'm not emulating the circuitry properly. But now the third new element that I need to be able to discern is, do I have an error in my firmware, which is the control ROM control logic. I've got some tests to write here. I'll be right back with those. Okay, so here's the tests that I am proposing doing. I'm starting off with several no-ops just to make sure that those work. Now, reality is that no-op is likely to work without any hitch. It's been executed so many times already. But then I'm going through each of the different instructions and creating an instruction to execute in the emulator. And then following that up with several no-ops just to give me a chance to see that actually flush all the way through. The challenge here is making sure that each of the control signals actually is being asserted when it's supposed to. So that said, if I start the emulator here, and I'm going to single step this now, I have several instructions into it, but that's fine. And so here's the move of an immediate value into R1. That's now in the fetch register, and that's now in the instruction register. I have control ROM 7 bit 7 and control ROM 9 bit 7, but there should be more than that. I believe control ROM 4 should have some signals asserted as well, and don't. I know that an instruction suppress should be asserted, and it's not. So this is just the first of many instructions that I've got to get through. I want to double check and make sure that everything is wired up in the emulator properly. I don't believe that this is... Well, I take that back. I don't know exactly what's going on with control ROM 4 because the value should be asserted here on these LEDs and they're not. I need to get to the bottom of that and find out what's going on there. Just to confirm, a move of an immediate into R1 as a fetch assert main. Fetch assert main is main bus assert fetch plus instruction suppress. And that has a complicated 7-bit value that needs to be asserted out onto control ROM 4, and instruction suppress is up here, control ROM 4 bit 7 as well. So I'm missing those, and I need to get to the bottom of that. Okay, so let's start with the easy thing first. What does the control ROM look like? And for instruction 0001, the control value is 93. That most significant bit was the instruction suppress. So that is control ROM 4 bit 7. And then the remaining 13 is related to the main bus assert of the fetch register. You look at this value here, 001, 0011, that's 13 on the lower 7 bits. So that tells me the control ROM is being built properly, so that's a good thing. Okay, next order of business is to check control ROM 4 to find out exactly what the contents are. So I'm taking a look at the SRAM, and if the SRAM is in debug mode, I'm just outputting what the contents of byte 1 are. And this is happening immediately at the beginning with the reset, and you can see it's actually got the right contents. So my issue is not with the data buffer, my issue is actually in something in the wire up, which is not necessarily a good thing. I've got to get to the bottom of that. Okay, let's give this a try. For the latch and the control ROM, what I'm doing is I'm outputting the value of the contents on the pins every time we have a rising edge clock signal. So let's take a look at that. And again, I'm going to slide this over and single step my way through this. So here's that move in the fetch register and in the instruction register. But I am getting 2 iterations here. In other words, it is signaling twice to process the clock. Where is that coming from? So in the control ROM, when it's processing the clock here, it's signaling the latch to process the clock state. And here, on the control ROM module itself, I'm also connecting it up to the clock. Let's get rid of this one. This one is the better one, not driven directly off the clock itself, but rather from the signal to the control ROM module. Let me remake this and try it again. Again, as I step my way through it, here's my move in the fetch register, and 9.3 in control ROM 4, that's what I'm actually looking for. I'm missing, now it appears, something out of control ROM 9, but I am actually getting the single latch. So now I need to go through and find out what's going on with control ROM 9 and why. Was it 9? Let's double check that. So this was R1 load, control ROM 9 bit 7. So I've solved one problem, I've created another. Well, this is the place where the linear nature of the emulator comes back to haunt me. Remember that the signals and slots in Qt are executed in the same sequence in which they're constructed. So the way I've got this set right now, my instruction register is constructed, and then the control logic midplane is constructed with all the components that are on that, and then my fetch register is constructed. And that means that on a clock, which all 3 of those subscribe to, the clock for the instruction is executed first, then the clock for the control logic is executed, and then finally the clock for the fetch is executed. And that is significant because that's the timing aspect of this where everything actually gets latched. So the instruction is going to get latched prior to the actual control bits being latched in the control logic, and then that is latched ahead of the fetch. And you would think that would be okay. So the sequence has bit me before, and you can see in the comment up here that their connections are critical. And I put this constructor here, or the construction of this object here, in order to keep that sequence correct. Well, let me show you what's happening here. And with that, I've stopped it. I am throwing out some debugging values here. And as I step my way through this, here is my move of an immediate value into R1. When I step it, I move it up to the fetch register. That then allows the EEPROMs or the SRAM and the control logic to perform their lookups and have their data ready in preparation for latching. This assert over here is what is going to be placed in for control ROM 9. But when I step again, the sequence is such that it actually reverts that back to a 0, and then I latch the 0 value, meaning that I'm not actually getting the proper data out here on control ROM 9. And even worse than that, there are interdependencies, basically a circular dependency between the control ROM, the instruction register, and the fetch register. What can I do about it? Well, I'm not quite certain. Full disclosure, I have tried several times to separate out the latch of the value that is on the inputs with the exposure of that new value out onto the outputs. And it's not worked out well for me. In the emulator, there's still some timing issue that I am trying to deal with and I can't. So I am not exactly sure what to do here, but ultimately this is not going to work because the value that should be on control ROM 9 is not actually being published. Now, control ROM 4 is good, control ROM 7 is good, but control ROM 9 is actually a critical one, and for whatever reason it's not latching the right value, or the value is changing at the wrong time, where none of the others are. I'm struggling to try to figure that out. This may be something that's buried in Qt, which is causing the problem. Maybe there's enough items that are subscribed to a particular signal that it is trying to do those signals asynchronously rather than synchronously, and maybe it's making that determination on its own. Not really sure what's going on with that. I need to think on this a little bit. I am not exactly sure what the end result of this is going to be, but I need to do some deep consideration on how I'm going to handle this. Next you hear from me in a minute or two for you, and maybe a day or two for me, I will lay out what that plan is. Well, the first thing I want to start with is the connect method that I'm calling. It has a defaulted parameter called connection type. Now it's set to auto connection, and that's what I'm using in my code. And basically it defaults to a direct connection if it's in the same thread. Otherwise it goes to a queued connection if it's not. And reading the description here, what I really want is a direct connection no matter what. But reading a little bit further down, I also found unique connection, which can be bitwise ORed with my direct connection, and it will check and report an error if by chance I happen to create that same connection twice. Well, that sounds like I can get my code to police my code for me and make sure that I'm not doing anything stupid. I'm a fan of that. So I don't believe that this is going to be the solution to my problem. It may be contributory, but certainly getting the oversight related to unique connection is a benefit. So I'm going to go through and update all of my connect statements to include unique connection and direct connection to make sure that I get that oversight. And then I'm going to test again. Again, I don't believe this is to solve the problem. I've got a much bigger problem brewing here, but I believe this is one step along the path. Be right back. Okay, let's give this a shot and see what happens. Now, I'm far more interested in what shows up down here in the output than I am on whether or not it actually works. Again, I don't expect it to actually start working magically. QAction Qt application. Unique connections require a pointer to member function of an object subclass. That's not a duplicate. That's a bug. I gotta go find that now. Okay, that just ended up being a specific member function as a member of the GUI application. And so now when I run this and look at the output, I'm no longer getting that error. Now, as I walk my way through this, put this into single step mode. Here's my fetch here. which contains the move. The correct value is being asserted for control ROM 9, but when I step again, it's reverting back to 0 and then it's latching. So I do still have the same timing problem. It's just nice to know that I'm not creating duplicate connections. All right, more digging, more research. I might have a plan. We'll have to see how this works. So in the clock module, I have a clock state that goes high and then low, and it reports that state out to everything that's subscribing to it. And what I propose to do is to change that into two signals. One would be a signal clock state latch, where anything that was taking input that needed to be latched would latch it internally, but not extend that to the output yet. And then the second signal would be a signal clock state output. And that would be responsible for taking the newly latched value and extending that out to the outputs. By changing the name of this function, or effectively eliminating this function, I'm going to break everything, so everything has to be revisited, which is good. But the default of what used to be should be the signal clock state output. And I think that's where I went wrong in my previous attempts, which I have not shown and I have failed previously. I had incorrectly equated that to be the signal clock state latch, and it really should be just the output. All right, let me get into these changes. It's probably going to take me a bit to get through these because every one of these that breaks has to be evaluated to figure out exactly what's going on, and everything that latches needs to have a new latch value added into it. All right, I'll be back with an interim update. Okay, honestly, I didn't expect this. Let me show you what I mean. As I get into this, I will step my way through. Here's the move of an immediate value into R1. Comes up here to the fetch. When I get into the instruction register, everything is working. My instruction suppress is even working, and when I step again, my no-op is actually what advances on. This is working exactly the way that I had intended it to work. Now, I only made changes to the 74HC574 octal D type latch. I still need to make changes to the 74HC74. None of the actual registers are hooked up, so the control signals themselves don't do anything. And then I still need to actually clean up some of this debugging code. So let me get the 74HC74 updated. Let me remove the debugging code. I'll come back and test again. And then I want to, and I'll do it off camera because it's going to be very boring. I want to go through each one of these instructions in this test and make sure that each one is actually asserting the correct signals. And all of that lines up. And then when I come back, then we'll start hooking up individual components of the emulator and see if I can't actually start executing something. I'll be right back with that. Okay, after going through all of my implemented instructions, everything appears to at least be asserting out onto the control ROM properly. Now there is an issue with jumps where jumps are not actually working properly. I had to move those to the end after confirming that all the signals were correct. But I believe that's a problem in the general purpose register and how that's implemented. And in order to do some more research on that, the best thing to do is to hook up and complete the wiring for R1 and R2 so that I can actually start moving things in there and see how that actually behaves. It'll give me a little bit easier time debugging. I'm pleased. I've got all of the control signals working properly. That tees me up now for my next video where I get to start doing some more soldering. But in the meantime, let me see if I can get the general purpose register sorted out. Let me set up some debug code. Well, the first order of business is to try to figure out exactly what to debug. To do that, I want to take a longer look at this load instruction into register 1. Now, I know all the control signals are correct here. I have an instruction suppress, but I should be asserting out onto the main bus from the fetch register. And the main bus itself has absolutely nothing on it. It should have the contents of the fetch register on it. The R1 register is loading, which is correct, but since there's nothing on the main bus, it's going to, in fact, load zeros. So the issue here starts with the fetch register, making sure A, the signaling is correct, and B, that the data actually makes it out onto the main bus. Well, that should be a simple search just to double check that I've actually coded that correctly. And then if I have, then we'll have to put some debugging code in. But at least now I know where to start. That looks better. I'm getting the main bus assert, and I'm actually getting data out onto the main bus. And when I step, R1 is actually being loaded properly. So that's a good thing. What was the problem, Adam? What ended up happening was I was updating the actual input pins, but on the 138 and the 238, I was never actually updating the outputs as a result of the changed inputs. It's a quick fix. Copy and paste problem. The problem was originally there in the 74HC138, which I copied to the 238. So let's see if we can't find something that's a little bit more interesting to try to test here. So let's try 042. That's not quite working the way it's supposed to. What I'm seeing here is that R1 is also being loaded with a 0 in between instructions, which is incorrect. So that should be just loading and persisting, but it's also being cleared. So I need to get to the bottom of that particular problem. That also turned out to be a relatively simple fix. Now, the fix ended up being in the counter, and the problem was the load signal was the entire duration of the clock cycle. It was not shortened to just the high portion of the clock cycle like the increment and decrement were. So here we go now. Here's my load. One is asserting out onto the main bus, and when I step again, it loads. When I step again, nothing changes in R1, which is the right thing. And now you can see the LEDs sliding to the left. I'll speed that up, and they slide back to the right. Now, when I wrote this test for the actual hardware, I only had a small number of bits associated with address bus 1, and therefore it would loop relatively quickly. Here, I actually have to reset it in order to get it to recycle its way through that. That's not a problem. And that actually is the first time I've actually been able to execute code in the emulator and have it do something, well, meaningful. I am very pleased with the end result today. Being able to execute code in the emulator is a huge milestone in this build. It basically ensures that I'm on the right track. Having to update the emulator for the clock rising edge to split that into two parts, that's something that I figured I was going to need to do. I had tried a couple of times and not succeeded, and that's one of the reasons why this video is so delayed. I was hoping to get it out prior to my vacation. That just simply did not happen. But I'm glad I was able to actually work through that and get that sorted out. I do have a little bit more cleanup to do related to that clock rising edge. It's really a cleanup of naming convention and readability of the code. And then I also identified a couple of bugs which now need to be translated into schematic and the PCBs. One of them is on the control ROM control module. I'm not going to respin that PCB yet. It's not a fatal flaw, it's just a flaw. And then the second one is on the general purpose register. I don't have a PCB designed for the reorganized general purpose register, and I'll do that as we get closer to placing that order. In the next video, since I've received all of the components and all of the PCBs related to the control ROM midplane, control ROM control, and the control ROM modules themselves, I am going to start building those out. So the soldering iron's coming back out again. I'm quite excited about that. To get everything built out, it's likely to take a little bit of time, so I'm not exactly certain if all of it's going to be done on video or if I'm going to roll up my sleeves in the background and knock a bunch of that out. But it's likely to take a little bit longer between videos, a little bit longer than I like between videos, just to make sure that I can get all of that captured or at least completed. With that said, we'll see you soon.